you were just telling me about mortal computers from Jeffrey Hinton gave you this idea about biological computers and how like biology seems to do this computation that's almost more efficient and more effective than the silicon kind of computers that we have today. So tell me about sort of biological versus silicon based computers and about mortal computation.
Okay. So the concept of mortal computation, just to review for those that are watching, is just the phrase that Jeff Hinton introduced in December 2023, and I had been in communication with him about that paper 20 days later and came out with my own. But the idea in that phrase is that when you have software, numerical calculations that characterize some version of machine intelligence, and in this case, he was focusing on machine learning. The idea is that we don't want to decouple that from the substrate or the hardware that implements it. So this kind of notion of mortality is that the software, when it is deeply embedded or entangled within a form of substrate, which in this case could be silicon, it could be analog computing, it could be a whole variety of things. When that software dies and it breaks apart, that software's gone. Now, what does that exactly mean? It means that in computer science, we all rely on the notion of immortal computation. And so, obviously, the opposite of mortal, which means you can die, mortal means you can never die. You think of something like ChatGPT or some GPT based program that's popular now these days. If the server or the GPU system that runs it breaks apart, fails, as long as we have that code copied somewhere else, we can basically put it on another server and it'll run pretty much the same. It'll do exactly what we did, especially if we even stored the weight tensors that encode the knowledge that was done through its training process with propagation of errors. And then we can say, hey, we can still do, for example, prompt-based query. So that's immortal computation. And actually, pretty much all of computer science relies on that separation that we can design software, that level of abstraction, without worrying how the substrate interacts with it. I mean, obviously, the more you know about it, the better and more efficient you can make programs, but it becomes very specialized. So mortal computation says, well, we're going to not do that, but why would we want to do that? And part of what, like, for example, my friend Carl and I have argued is that there's a thermodynamic efficiency that is afforded by appealing to the mortal. And in a very, very simple way to put it, we are trying to bring, if you don't separate the hardware and the software from each other, you bring the software as close to the hardware as you can. Whereas in modern day computers, the von Neumann architecture you and I and everyone else is very familiar with, we have levels of memory, right? And we store the tensors of our GPT, ChatGPT program in long-term memory. And then we start to transfer it to shorter and shorter terms of memory, more volatile memory, until we get to the CPU. And we can run our calculation. And that calculation isn't so bad compared to the cost of transferring this information back and forth between the CPU and long-term hard memory. And there's an energy expenditure. Every time you go through it, there are picojoules of energy that get emitted. So inherently, when we work with these types of systems, we're losing a lot. And that is why GPT and large language models and modern day deep learning is extremely energy efficient. Actually, even in like the one paper that Carl and I wrote, it's like almost like the carbon footprint of a small city used to power some of these big things, which is ridiculous. Whereas mortal systems, and again, you could look like to the human brain, only use a few watts of energy to conduct very complicated computations. And so the idea is that we want to bring the compute really close to the hardware or in-memory compute, and that's very energy efficient. And that's a good starting point, and I'll leave it there.
Right. So the immortal ones are inefficient because you said efficient, but like so that they're inefficient in the sense that right, you're gonna have to constantly go from where it's all stored and then take that out of memory and then start using it. So if I
Mhm.
understand it, that's how the computers we typically use today work. We want to like design. It makes me think you want to design programs or you want to design AI such that you can take that and like put it somewhere else, right? So you don't like you can then put down other computers around the world or like you're not reliant on the specific GPUs you have. I mean, it's a weird idea, even model computation, that the code would be like reliant on a specific hardware. But like at the start, I brought up biological sort of entities as like a form of mortal computation, just because I assume that like there's really no way to move the things we're doing away from the body that is us. I mean, is that right? Like, tell me more then about, yeah, what modal computation is, what this alternative way of thinking about computation would be.
So it's a good question, and it gets beyond. So what I gave is sort of the easier to digest AI community argument, right? Because the argument's going to be, why would I leave GPT and backprop based learning for something that is going to have these inherent limitations like tied to the hardware? So energy is a good argument. But part of computation, and this is again what Carl and I have done here, is it's much more than just the energy expenditure. It's all about identity preservation. So the other part that, again, Jeff only really was referring to at a loose level, the energy efficiency, the interpretation and direction that I've been pushing for is that it also tells you how intelligence and sentience and behavior all really come from this inherent notion that you don't want to die. So death and life, two sides of the coin, are important for even just any entity, and it can explain a lot of biological life, and then we can apply these principles to non-biological life or artificial life, as we discussed. But really, at the end of the day, your main objective, whether you consciously or even thinking about it, and humans are quite complex creatures, and we have a lot of other goals and objectives and things that are laid on top of each other, all stem from where we originate, which is we don't want to disintegrate. And what do we mean that? That's a physics way of saying that we live in a heat bath and we become heat, right? We are essentially entropy, we increase and we break apart. And so that's thermal equilibrium, and human life, and actually just life in general, is thermal inequilibrium, or they want to remain from equilibrium. The idea is that if we don't want to reach that point of our identity dissipates. And so the key here, and like you were saying earlier in your comment about the body, that the body and further your environment and a lot more than that, if we can talk about that if you want later, basically shape your specific computation, your identity, your organizational and functional operation, but also your quirks and eccentricities, if I'm saying that correctly. They basically make you Jack who you are. You are shaped by a lot more too than just your body. You're shaped by environment, and these are really what. And when you die, even if, like for example, we could somehow take your brain or what we would call some copy of it and put it in another body and say, well, Jack will live, you won't be the same. Because, for example, your digestive tract and your other aspects of your biological function, your thinking. I mean, we know this in so many examples, and I could go on and on and on about how your biology impacts your thinking, and that's just one thing. So that's kind of what modal computation does, is it takes the energy efficiency argument, which is appealing to just try to, tell the AI community, maybe we're not going down the right direction. I am one of those people. Maybe we should think of other directions, and this might be a promising place to go. But it's so much more than energy efficiency. It's all about self-evidencing, as Carl's favorite phrase, and I like it as well. You are trying to find and optimize evidence for your own existence. That means you have to forage for resources, nutrients, and materials so that we can also remove toxins and waste from your body, all in the service, at the end of the day, to avoid disintegration in your death. You do not want to lose your identity. You must preserve it. And that's essentially what characterizes life at all levels, ranging from like E. coli and simple bacterial cells all the way up to very complex animals to human brains.
Yeah, so it's interesting that the fact that, say, me or any kind of biological human might die, there's that fact that you need to persist, but it's actually difficult. That to the degree you say one's doing computation, that kind of fundamentally changes the kind of computation we're doing compared to, say, the kind of silicon immortal computers that we're making today. Like I was reading a book recently called "Your Brain Is Almost Perfect," by Reed Montague, and it's kind of like the fact that we care about the world means that we can run this biological computer on like a banana, and it's whereas the other computers are just, and so, but it makes me wonder. I mean, why with a computer that we make, does it need to like try and actively not die, like to what degree do we need to make them to replicate us? Like why can't we try and what ways can we get their efficiency higher and make them as like effective computers, so to speak, as us? Like do they need to have this risk of like death that the biological systems do in order to have that efficiency?
So my hypothesis, or rather the mortal computation thesis, says yes. It does need that imperative. It maybe doesn't have to have it in the way that we have it, which is the idea of death, like, oh, well, homeostasis specifically ceases, but it needs an imperative fundamentally to want to preserve its identity. And again, there's many ways to discuss what identity means, but one of them is something called functional organizational closure. And again, in like the paper that I had you look at as well, that Carl and I wrote, one of them is dynamical systems or self-organizing systems, and humans are an example of such a system. We are made of many little parts, and these little parts work together to create higher level entities or higher level units, and then those entities farm together, and we get this big multiple time scales in ever-growing hierarchical, or rather heterarchical systems that are very complicated. And these systems themselves, right, are trying to avoid, trying to reach states of stability. And that's really the goal of any optimization perspective. So it doesn't necessarily have to mean that it understands it in the sense of like, my biological function will cease. But that functional organizational closure I'm talking about is the relationships between the parts, not the exact parts themselves either. And this is another interesting dimension I just like to introduce in light of your question, which is your cells die, right? Every so often. You are not exactly the same Jack you were a few days ago because you're constantly in this process of birth and death, renewal and regeneration and degeneration. Cells die. They even have programmed death. And then they have, other aspects that they are trying to remove toxins and things, decay and growth. And so the fact that your exact morphology, which is the other term that's kind of part of this, is changing over time, you're still Jack. You still have the same rough thoughts, the same kind of quirks of your computation or cognition. And that means that your organizational closure, your relationships between all those cells and what constitutes your biophysical, as well all the way to your actual mental identity, remains roughly the same. You change with time, but you still are. And so that kind of idea that all the things that you do, whether they are conscious or subconscious, because again, I am allowing for complexity here, because you might not be thinking right at this moment, I need to drink a glass of water because I'm going to die if I don't get enough water into my system. Your body will just do that for you. There's a lot of subsystems that make up Jack that allow you to keep doing that. But that would also apply to mortal computers of any kind. They must want to preserve their organizational closure. They must not want necessarily to disintegrate, to lose the knowledge and aspects that they have encoded of their information that they have encoded in their environment. And that means that they're going to act such that they preserve that identity, which kind of gives you for free, and this is from a machine learning, machine intelligence perspective, a wonderful goal. And it kind of even gets into, I don't know if you're familiar with reinforcement learning. I know you have an economics background, so there's some nice game theory connections. But from the reinforcement learning perspective, and that's a big aspect of AI today, we design these little reward functions that are very task specific, require the human to reward engineer something very intricate and important in order to get good performance, because we care for very important test performance agents. But you have this problem of exploration where it needs to understand its environment. And so this idea of identity preservation kind of gives you for free an objective that allows the agent, even without a task, because you still do things even if I don't tell you, we need to, chat about this topic, or I need to answer, you need to ask me questions and I need to answer. You're going to such that you move about your environment, you information forward, you gather things, again, constantly optimizing your own evidence for your own self, right? Because again, everything you do is an avoidance of disintegration. The argument here is that a fundamentally new paradigm and direction that all of AI research and machine intelligence and complementary fields should go is in this direction, where the foundational imperative is essentially to preserve your identity. And my final comment on this is that we see this as a grand unification of even like biological research, physiological, biophysics, chemistry, things that have echoed over the last century. And this is what Carl and I have written at length. We're not the first to kind of talk about the idea of even homeostatic compute. But this kind of explains even why very, very, very simple organisms do what they do. Because again, to preserve their identity, you might not know it. They might not, explain it to you in any way, but ultimately they are trying to avoid dissemination. And so I think that machine intelligence needs to recalibrate and essentially go in this direction. So yes, very much so they need that aspect of humanity. We might not need to call it biological death because again, they might not be biological, they might be insulin.
Yeah. So it's interesting. It helps me understand it that imagine with the AI like today, we need to, from a top-down perspective, we need to go and give it goals, and then it kind of tries to maximize that reward function we've given it. For us, and for really complex systems that need to preserve their own identity, they're kind of constantly having like layered goals of like, because they need to constantly do things to try and preserve what they are. And that kind of makes me think of even like babies, and it's just like even just letting them be there, they're gonna be doing things to try and and they're gonna start crying if you don't get the right rewards, but like that's gonna push them towards learning new things and gaining things to help them sort of persist. It's interesting then with computers like today. I mean, is there any, what if we make like, what would it practically mean to try and have mortal computers? Like, so like it makes like, I want to then ask like, maybe even first, do the immortal computers of today, like tell me a bit more about them, like for example the AI that we're making today, saying large language models, because I kind of want to understand like why, to what degree don't they have this necessary complexity to sort of be trying to self-persist, and what would take them to that level of mortal computing?
Sure. I will, before I give the answer to that question, I will put one important caveat that I don't think let's call it the technology or the approach that we do to transformers will be what goes into the final biomimetic entities or mortal computers. But you could imagine trying to use backpropagation-based methodology, even if that's not what the brain is. So I have my, let's say, hesitation about transformers, but that's my comment. Now, to answer your question, even why transformers or even just modern day machine intelligence doesn't have this imperative I'm talking about, there's a couple of places you could look to, but I think let's start with another aspect that Carla and I have talked about, which is embodiment and enactivism. So again, we've talked about the energy efficiency, and I think hopefully I've sufficiently convinced you that at least the way that we do compute today, things are very thermodynamically inefficient. There are ways around it. We could talk about that if you want to. You could poke at that. But embodiment is this idea, and it comes actually from cognitive science and naturalist philosophy, is that your body itself is a form of your mental functioning in cognition. And what do I really mean by that? It means that your mind is not this isolated brain in a, which is actually an old classical psychological kind of view of the mind that says that your mental functioning, things that you do, your thinking processes, right, are independent completely of anybody. And all that the body is just a place to sit. So you could have a brain literally in a vat, and it would be as human as anyone else. It just wouldn't have, our particular sensors and motors and actuators. Now, embodiment says that's not true to varying degrees. And there's a bunch of embodiment theses out there as well. But some of the more extreme ones, which again, I tend to lean towards, or mortal computation leans towards, is that you actually offload thinking and cognitive functionality to your body without even thinking of it, because it actually helps reduce the burden on the brain and allows you to do other processes. So for example, when you're walking, you're not necessarily thinking every step in time, how do I move every individual joint and to move my foot into a particular next step? Your body kind of has this biophysical architecture that will naturally do things like to use computer graphics, inverse kinematics, right, to move about your joints, such that your brain can execute a higher level program. And again, it depends on where in the brain you're looking. I'm kind of simplifying it quite a bit for any neuroscientists that might be watching your podcast. But the idea is that it's executing a command saying, go forward, right? I am doing some path planning, or I want to get to point B from point A. I'm not necessarily thinking about how my joints and my legs and my architecture, my biophysical architecture is going to manipulate itself and interact with gravity every single millisecond of time. That would be intensive from a computational point of view, from your neurophysiological architecture. There's a lot of other things that you'll be doing, again, in order to ensure you survive. So your embodiment, your body is actually doing computation, and it again, out there's the subcircuits, and your nervous system, for example, offloads a lot of this compute that your brain can say, execute this high-level program, and then it transmits across, and your body will execute those subroutines, right? So that embodiment is very important because that, again, is shaping what your brain knows. And there's a lot of cognitive evidence, for example, that we have sensory-driven dreams and thoughts when we try to describe objects. They are obviously based on our bodily experience. Like you said earlier about babies, why do we put things in our mouths or grab things and throw things around to understand? Babies are wonderful physicists trying to understand from an intuitive point of view how to knock things over. Well, that's all because the body is allowing you to form an impression, right? To encode that information from your sensory modalities, which could be vision, sound, taste, touch, smell. All these things are what the baby is using to try to build what is known as a generative model of its environment. So that's like one other part. The other piece of the story, and I'm glazing over a lot of other nice little details, is enactivism. So enactivism is saying that, so you have the body. Let's say you buy my argument that your mind and cognitive functionality is grounded in your body and you need a body. That's great. And your body, by the way, changes how you do things. If you had way more than 2 arms and 2 legs, you would have different programs and routines that would allow you to navigate the environment. So your environment also shapes what you do. And there's a bidirectional relationship because, again, depending on your niche and what resources are available, you're going to behave very different. If you have a very hot environment, a lot of, for example, animals seek to find areas that are cool, right? Because it's not good for their temperature balance and their chemical composition. So your environment, it plays a very important role in shaping what you do, and you also shape your environment. There's a bidirectional relationship here. You change your environment with action, which comes from the notion of inference, the idea that we actively perceive our world and manipulate it, or rather a good phrase to this is we create order by generating disorder. So the idea is we're manipulating our environment such that we serve our imperative. Now, to answer why all of that is what's missing, among many other things, in modern day machine intelligence. So ChatGPT, again, like I said, from a thermodynamic point of view, if this GPU server fails, inefficiently, you can just put it on another server and it'll do the same thing. Well, then that means it doesn't have a body, right? It is a brain unit, if you think about it from a software point of view. There is no embodiment. There is no notion of, this is also why, for example, machine intelligence struggles in, I would argue, the ultimate domain to tell you how far we have yet to go, which is robotics. And this kind of gets into some interesting things we could talk about AGI, but the idea that you have no sense of body, no sense of a niche or an environment, ChatGPT doesn't understand. So it's an hint, right? Because we are inherently grounded in that interaction, in that form of existence. And that's another piece of what's missing. And there is some attempts to do that, but when you just try to put in our typical software in some robotic system, right, and hope that it works, well, there was no notion of designing the compute to exploit that, right? It's just more like we're plugging in a bunch of electrodes into that brain in a vat and saying, just control the system and that should be good enough. But if you don't understand how to control your body, sure, you probably could learn, but it's learning a lot from scratch. And that is my final comment here, the role of evolution, right? Because we also have a long trajectory. Humans didn't just exist yesterday. We've evolved over time. And so there's a lot of inductive biases or priors that have been instilled in us that when we're born, sure, there's a lot to learn as a baby, but we can recognize faces. And that's very important for that baby's survival. It needs to understand, who its mother is, right? It needs to understand that, well, I know how to cry. I just don't know why it's useful, but it knows that it can trigger that. It doesn't have to try all possible combinations of its internal vocal cord circuitry to try to figure out how to make a cry, right? So all of these things allow you to get really quickly out of the door when you're born to survive, or doing whatever it takes to try to get other resources and manipulate environments. So ChatGPT has no design or any intricate understanding of its own embodiment, let alone its niche. And so that software is inherently separate and different. This is also why we can train things like with calculus, backpropagation of errors. It doesn't care at all about the architecture. It just says, I need differentiable functions. As long as you got that, you could do deep learning. I can keep going, but I think that hopefully makes sense.
So it's cool that something I thought about kind of recently is the fact that through evolution, not just in the whole history of humans, but even then beyond that, the fact that in a way it's a kind of learning, kind of training of who we are to just be super well fitted to our environment as that changes. So you kind of miss out on that. And so it's interesting that with LLMs, and then we try and miss out on some of the things that humans naturally have to help us learn, and that allow us to be so as complex as we are. I mean, I guess LLMs weren't made to be in robotics necessarily, and unless I'm wrong, and they did not. I guess no one made them to make them like biological computers. I remember I had someone from Michael Levin's lab. We talked about spiking neural networks and things to what degree are these weights and these simple things we do in the machine learning, are they actually like biology? In some ways, they're not. So kind of intimated that there is. So is there differences in kind that LLMs, as cool text as they can make, as cool images, are there limits to actually what it can do through going the route that it has? Then is it just efficiency gains from model computation, or are there fundamental limits that if you don't try and replicate the kinds of things that biology does, like an activism and embodiment, that you just can't get?
Yes. I mean, the answer is simply yes. There are some things that I don't think you can do. And I'll add the other caveat that there's a lot of interpretations of what a body in a niche could be. It doesn't also have to be, and I want to make clear, it doesn't have to be like a humanoid, for example, body, and it doesn't need to be like planet Earth like environments. The internet, for example, could be an environment, and there could be a digital agent body that interacts with it. So there's probably a lot more interpretations that even possibly add. And I want to add that caveat to say that as long as you have designed some sense of body, and that software is entangled, right, and designed with that body and that form of interaction in mind, you sort of do get some of the aspect of mortal computation. But there needs to be that notion of essentially death, right? Or that notion of disintegration. So those agents need that imperative to want to not be turned off or destroyed. Whatever that might mean in different environments is going to change. And so I can't possibly elicit it. So that's one comment. In terms of the way that I think mortal thinking or biological intelligence or biomimetic intelligence, as Carl has gotten me to sort of call this kind of area, is that part of the difference between the way we do artificial intelligence work is, and this is like a big distinguishing factor, we tend to design towards a task. We have something in, there is some work on multitasking, sequential task learning, but that's a very, very wild frontier, and I think we have a long way to go to make progress on that, which actually might be important. I'll bring so when we design something that's very task specific, we have something called narrow. So we can get something that classifies cats and dogs for you, actually even at superhuman levels. Like it'll do a better job than you do. And we have seen plenty of examples, and that's great, right? I mean, these are useful tools. And by the way, I also want to make sure when I'm adding all these caveats, because I don't know what kind of audience watches the podcast, but I don't want to say that propagation-based large language models or deep learning architecture are useless. No, they're very useful, but they're useful for tools. And so we build them to solve a narrow application, and they do their job, and that's great. They are passive, and they are reactive in the sense that we tell them what to do. We say, we want you to classify cats and dogs, and that is it. The system did not choose to classify cats and dogs, right? It did not have any drive to decide this is what I need to do for whatever reason. It could be like I was trying to say for survival, but it never had that impetus to do what it decided to do. And our reinforcement learning tries to get at that, but again, it's always a goal-driven reward, right? It's something that we shape the behavior. The entity did not arrive that it should, for example, make you a cup of coffee because that was good for its friendship with you, because in the collective, it's good to have interaction. That's good for survival. Again, we can always tie it to survival. But so the idea is that AI today is designed from this tools-oriented perspective. That's very valuable, but it's not going to lead us to the general intelligence that we write in sci-fi or that we seek. So from the biomimetic point of view, the biological idea, having this sense of embodiment, having this notion that the environment shapes what you are and that you interact with it and you are coupled to it. By the way, this goes beyond this, and Carl and I have written, it goes into, for example, other mortal computers. Like you and I are mortal computers, and there's a lot of us. We live in a collective of mortal computers. We create culture. We create, for example, social interactions. That influences a lot of things that you do. And then the final piece is called theory of extended mind. You use calculators. You write on a pen and paper. That's part of your mind as well. It's a non-mortal object, so it's not a mortal computer itself, but it is where you offload your cognition. I use a calendar, like I track today's podcast with you. Without it, I would have forgotten, even though I would have been sad to have missed it. So my mind is also part of my non-biological objects. And I think that thinking about designing systems, taking these aspects into account, which is very complicated, I'm not saying that this is an easy switch or an easy direction to pursue, would give us things that allow us to generalize, I think, differently than the way AI does today. And my final point on this is, like I was saying earlier, we train things for one single task. What about many tasks in a row? You can breathe, and you can also, for example, hold a podcast interview, right? And because you're talking to me, you're not forgetting how to breathe. And this is called, memory retention. And in machine learning, this is extremely difficult to do. We have a problem called catastrophic forgetting. You train a deep neural network how to breathe, and I'm loosely making this example as a cartoon example. And then all of a sudden I say, let's train it to do question and answering, to conduct a podcast interview with, and it's going to be able to learn that, but all of a sudden it forgets how to breathe. Now, again, if it is a mortal entity, it would die, but let's just say it can't actually remember things, and it's even when you build in memory mechanisms. And so the reason I bring biomimetic intelligence as an option is that it can offer you mechanisms that are just not around today in the traditional artificial intelligence community. And I think by having constraints, which is the final message of biomimetic computing, because you'd say, why do I want all these constraints? Because biology is messy, it's constrained very heavily, it needs to do things in a very particular way. And I think that is what also brings about powerful generalization, because when you're forced to say, I have these cards that I'm dealt with and I have to make them work, you get creative. And biology and nature itself is very creative. It is, evolution's a random walkish kind of process, but at the end of the day, we find these very efficient and intelligent ways to solve that problem. And then that's what gives rise to a variety of the complexity and diversity of life, because not all biological organisms attack problems in the same way. Again, you could talk about sea creatures and the mechanisms that they have to allow them to adapt and persist and thrive in their niche. It's very different than what us mammals do on land, and what allows us to persist and thrive in our niche. So I think that these constraints, while they might at first feel problematic and brittle, I think bring about them the challenge to actually design truly generalizing systems. Now, again, generalization in this case won't mean that the mortal computer that let's say you build a mortal robot that can, swim and it can deal with aquatic life. It's not going to work very well when you bring it out of water. You're not going to build these general purpose computers that can just go on any environment, create, a niche agnostic kind of entity. It's going to be very specialized for the body that you give it, the physics constraints that it has, the thermodynamic costs of, for example, energy expenditure of moving its particular set of limbs to propel itself in the water, and also the water environment. It's going to understand the flow of the liquids, right, that it moves through. It's going to have some sensors that are very specialized for that, and it will know how to take advantage of that and design, calculations that allow it to manipulate cleverly its environment. And so it'll be very powerful, far more robust and more general, I think, than any ChatGPT thrust into an aquatic robot, but it's not universal. It's not going to be able to solve any problem. It'll solve its niche very well, which is what we humans are. We are not we do have technology to go underwater, but we are not naturally built to just swim in water for long periods of time, as well as some of the fish. So I think that's kind of the value that biology brings you, is it brings the beauty of constraint to allow you to get creative, to design general systems that can solve those problems and those thermodynamic tests, if that makes sense.
Yeah, it's interesting that you talk about the AI today is kind of specialized in certain domains, and it's interesting then in like reflecting on what benefits that gives mortal computers. It's kind of like you can't necessarily always define every single domain. Even like imagine you're trying to run a body, you can say, oh, you need the heart and the lungs and how to speak, but then there's almost like always intercategorical, like again as John Vervaeke, the cognitive scientist, talks about, it's like it's actually not obvious how to solve any problem. There's not even obvious how to sort of define almost the whole point of cognition is in fact postulating what kind of problem you need to solve. So it's not actually obvious what like a problem is, and it just that makes me want to then ask, like, to what degree do we want or need these kinds of AI, in the sense of, I guess, with maybe large language models, we're kind of saying like, hey, it would be cool if, like, we got like text that was like, kind of related to what we said, and they can solve the code we want or the question we want. What kind of things would we want?
You mean like applications?
Yeah, well, like applications. Yeah, like we okay, cool. Actually, not only are these model computers more efficient, like we're gonna make them because actually it's gonna be able to do like fundamentally different things from the kind of AI we have today. What kind of things would we want them for?
So, okay, there's really interesting applications, and then there's, just to even answer your initial one, which is more of a fun application. So those chatbots that we talk to, or those that we discuss, they're trained on loads and loads and loads of internet data, right? They are also an aggregation of the collective of humanity. And my own personal joke to my colleagues and friends is that these are very schizophrenic systems, right? They don't have some unique identity or personality. They are an average of the humanity's experiences. So imagine if you had an embodied, we'll just go ahead and say a transformer, but an embodied machine intelligence, and that was your chatbot. Well, you would be talking to a unique individual. It might not be a human, right? It would be a different entity. It's a different species, if you will. But it would have its own sense of experience, right? It would be grounded in its own understanding of the world. So when you talk to it, it would have a beautiful sense of consistency, right? Again, there are inconsistent humans as well, but it would be consistently inconsistent if it were that. But the idea is that it would have some experience. And when you ask it questions, and I mean, now again, this might have gone away through a lot of constraints and what research does. But in the earlier days of chatbots, as I worked in the era of recurrent neural nets and things before transformers really came and wiped all that out, those chatbots had this problem where you could ask it, are you married? And the system would say, yes, I have a wife. And then you'd say, oh, what is your wife's name? And it would say, I'm not, something like that. It would have a contradiction. It would say, I've never been married all my life. And you'd say, well, wait, that doesn't make any sense. Where's the consistency? The context isn't even maintained. And you can hack it away and you can make some things, but at the end of the day, there is no like fundamental identity that this thing can express to you. And when you ask it its questions, it bounces it back its answers from its own perspective. And also you would have different experiences with different chatbots. So you could have a infinite variety of different individuals. So that's even from like the chat point of view, I think could be very interesting, because that could also then improve, for example, how chatbots interact and try to help you do tech, for example, instead of just having kind of these generic averaged experiences, maybe you have ones that did actually work with the tool that you're struggling with. And that would be wonderful. And then those are the people that are your experts, right? And so I think from that little point of view, you'd have dramatically improved interactions with these entities. And it doesn't have to be through text, but that's an easy example. Now, the more interesting, complex examples, and I think where mortal computers really, and we do, by the way, have some mortal computers in existence. And the work that I did with Carl highlighted some, two of which now come from Mike Levin, which you interviewed. Xenobots and Anthrobots are actually mortal computers. They're beautiful examples of them. I love Xenobots, but without going into all that, because I'm sure you guys might have talked about that, the idea is that with these types of systems,
say a bit about them. So, like, because you create these artificial biological, like, I don't know, entities. You take them from biology, and so like, there's seemingly biological cells. But tell me why you think they're mortal computers.
Well, they have, for example, so like, let's say xenobots, which are taken from frog cells and kind of carefully stitched together to create these little teeny biobots. And the beautiful thing about these is they can form collectives. So they can specialize and form like spheroids that can then be generalized to different little, you could call them like motor systems and submotor systems, and they can learn to solve complex problems already. But the other thing I really love about xenobots and anthrobots, which come from tracheal cells, which is a much more recent innovation from Mike's group, is that these things can self-repair and they can repair from damage. And of course, they require nutrients like us. They can die. And Mike's group has done experiments where they have shown like they can live for so many days if they have like a nutrient-rich environment. So you have to feed them just like anything else. But assuming that they have that right environment, they can heal, they can repair. And that, I think, is something completely unearthly and different than what you could do with today's modern machine intelligence. Like, again, even if we could give a transformer or a deep learning architecture on a GPU server control over its, let's say, server, and it got damaged, could it repair it? And another piece to the what we didn't know, and the answer is no. And in the work that Carl and I did, even from a silicon perspective, we need to give Ross Ashby some love. He has this wonderful invention long ago called the homeostat. And the joke of the homeostat, it's just like an artificial system that remains in equilibrium. But the thing that's cool that they said, this computer can do something that no other digital computer can do. It can survive a wire. Because if you cut the wire on your computer, it's gone. Whereas the homeostat actually would work around damage that it had, and it would be able to persist. So it's fault tolerant. And so again, xenobots and biobots are the biological analogs to the homeostat, if you will. And so that wonderful form of morphogenetic adaptation, I think, is so important. And that can tie your comment back into your original question, which is the applications of these. So in Mike Levin's group, and I think it's a wonderful place that I think could revolutionize medicine, is it can be reparative. Right? It can, for example, repair damage in your own tissues because these biological entities are more likely to actually play nicer into the wet environment of your biosystem, right? Your body, and it can actually repair tissue. And they've actually shown things that they can actually repair them way better than any surgeon can. And then they can also disintegrate too because they can die, which, if you have any feelings for them, that's sad. But once they've done their purpose, they disintegrate. They just kind of like go off into the environment and they're gone. And so they are the most ultimate way, I think, to do regenerative medicine. And this gets into even more applications, like you could think about the notion of cyborgs, right? And how that ties into making humanity's quality of life improve dramatically. We could do all kinds of things like, for example, create semi-biological or chimeric constructs like eyes, like replacing eyes that can help repair damage in your cortical region. You can also do things that improve, for example, your own biological efficacy in the environment. For this one is kind of weirder. Maybe it's not so biological because the body can be, for example, chimeric or hybrid, right? It can be multiple things. Exoskeletons, I think, are an interesting place to look because, and there's been some really good work already about, like, for example, artificial limbs allowing you, for example, to react to feedback. So these little entities, right? Like give you your interface with your nervous system, which requires kind of some knowledge of the actual biology of your body that can allow people to walk. And exoskeletons can give you strength that you've never had and allow workers, for example, in factories to work longer hours or rather reduce stress or strain on them. And they can actually do tasks which, without hurting or damaging their health. And I think these are things that you need to have an understanding of the niche, because even if those entity, the moral computer doesn't necessarily even itself need to do its own thinking. You could be pairing it up with a thinking entity itself, but it needs to have this idea of, biophysical interaction with its own body and its own coupling to its own environment, and then we've offloaded some of the cognitive functionality to a human. But I think that's like one of the best places, probably the earliest places I foresee mortal computers coming into play, is augmenting humanity rather than creating a completely different entity, because I think it gets harder and harder to build more and more complex mortal computers. Very simple ones be paired up with us in a beautiful kind of symbiosis. And I think that, and again, medicine, I think, is one of the most important places. And I think like the work that Mike's group is doing is wonderful, and I hope only the greatest success to come, because I think that could help us.
So that's amazing. And it's also very useful because it's, again, not easy. The idea of mortal computers and like thinking about these as a kind of artificial intelligence is not really something we've done so much. Where, and like I want to then contrast that, we were doing it the whole time, but contrast that a bit with LLM, say, which I guess people will be more familiar with at the moment because they're so popular and stuff. Is that, you talked about how like they have these problems, like they hallucinate and things, are a bit schizophrenic. But then you say, oh well, they overcome that problem because it seems the way they overcome that problem, and tell me if I'm wrong, is that you kind of just make them bigger and bigger. If you put more and more compute power, it's like you can push away a bit of the flaws and it looks all right. I don't.
Or you constrain it manually as a human, so they put guardrails, right? So okay. I have another joke. Let's see if I can present it in a politically careful environment on the internet. So when they trained the original GPTs, and you train it on internet data, there's a lot of unsavory content, and this is how I'm going to put it on the internet, right? It doesn't matter your political leaning. There are things that are really immoral and really bad. And some of the earlier chatbots parroted it because, again, one thing that these things do is they overfit quite heavily to their data. Again, when you make more parameters bigger, as you said, it gets better at memorizing the data and the noise. And it's a principle called overfitting in machine learning. But and so you give it all of the internet, it's going to be very good at becoming an approximate, I'm not going to call them this exactly, but lookup tables, right? And they can learn to kind of patch together these different pieces of information. But at the end of the day, they compare anything. And there's a lot of things they can get to that we don't like. So those unsavory parts of the internet, what we do is we constrain them with guardrails, and we have humans go ahead and we have them interact with them and traumatize them deeply, is what we had found out from some tech companies that had offloaded some of this crowdsourced labor in other nations. And I'm trying to be as vague as I can here without making any direct attacks, as I don't feel interested in engaging in that. And these people were traumatized, but what they did was they were able to say, oh, we probably don't want it to say this, and we need, this is bad, this is good, this is acceptable, this is unacceptable. And then they can include these constraints to prevent the system from saying these unsavory or going down these unsavory paths that the internet gets you to. So what we do is we heavily engineer guardrails to kind of tailor the experience, because there's a lot of marketing that goes into these transformers. Rather than, you are right that you can train it on more things, but I think training on more things risks also polluting it with, again, since we're aggregating across all of humanity, right? You're going to start getting things that might not be what you want, and that's part of the effect of the hallucinations. But it's also why, for example, these things give you nonsensical answers. Like more semi-recently, the people were like querying Google's engine or its chatbot, and it was starting to give them Reddit answers to their questions, like how to make certain foods, and it was saying we should put glue in. That would be a very good ingredient, right? Why? Because these things also get attached to very salient pieces of information. So there's a particular kind of information or the perspective on the internet that's going to be very emphasized. It's like a weight, right? A probability in the model itself. And so the only way they can counter it is kind of what I was saying from mortal computation, where we need to encode biases, but I think those come from evolutionary processes. We encode our priors by saying if statements, right? kind of like prevent it from saying certain things and checking it. So the capacity argument is part of the story, but we end up having to do a lot of engineering to prevent them from devolving.
Well, that's really helpful, because I mean, part of the reason. So you kind of talked about their flaws there, but I kind of wanted, because like a reason I brought them up again is actually, I wonder if you can say that mortal computers would be more efficient and more effective and be able to do the kind of things that these LLMs can't. But then I think about people talking about, well, maybe these LLMs would get to like some kind of super intelligence. So hey, they're super inefficient, but if the people that make the most, they turn the internet to such a degree that they, I don't know, find the secrets of the universe, etc., then they won already. I don't know. Tell me about that. I mean, and as well, other things hidden, maybe even in language itself, like that they can have some kind of understanding that we don't realize, or we think it's just the internet. Tell me a bit more about that.
Well, okay, there's a lot of different pieces to your comments and questions there. I would say, I guess to kind of tie in our last discussion about bigger is better, which is a typical argument, and without the poisoning argument and the data problems and the hallucinations I was explaining, there is an argument that the bigger these systems become, the more likely they're going to solve problems. They're going to become artificial general intelligence. And I think that's a little nonsensical, because while the brain is composed of billions of neurons, trillions of synapses, so there is that kind of scale of complexity, which is needed, you have to look at the individual computing units. And I think that's the problem that I have with deep learning in general, is that even our neuronal models are pointwise, right? They are just literally weighted sums of incoming signals, and you chuck them through a little function, a nonlinear function, to give it some nonlinear behavior, and you learn the weights along those incoming edges. And it's gotten us pretty far. I mean, we have some really nice applications. Again, just a comment, there's not like it's useless. But these computing units are so unbelievably simple. And I think that that's the inherent reason why you need more and more to get the generalization that you want. It's like this inefficient use of your capacity, because I think of cognitive science, which has this premise of building cognitive architectures. And what is a cognitive architecture? It is a theory of mind. Now, again, it is a theory or a hypothesis, and it can be wrong. Many times they are, but such as science. But when you have these architectures and these particular modules interacting with each other, you are trying to ground them in known memory mechanisms, for example. And you are building a parsimonious architecture that tries to get that functionality that you want in an efficient and grounded kind of way, whereas a lot of connectionists is what they used to be. Deep learning architectures today is, if I just do more, I can somehow learn different tasks, and they do, right? Actually, there was a really interesting discussion at, I believe it was AAAI, the keynote that I was at, where the guy did an experiment where he built a little transformer, and it didn't do well at all. It failed on most of its experiments. But as he gradually increased its complexity, more layers and more neurons, there was like this point where it reached like 1 billion, and all of a sudden it could start doing many tasks in a row, which was really interesting. There was like, it needed that complexity scale. However, and of course, then he said, so that's why bigger is better. And we need way, 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 way more. And then we can just like learn everything that a human can, or all of humanity. But the way I look at it is without any bias. And cognitive architectures have this beautiful bias, which is modularity, right? We kind of have specialization. We humans, when we design a cognitive architecture, we're playing the role of evolution. We are saying we're going to skip simulating many millions of years of evolution. And we're just going to get to the result that we're like, well, okay, this entity seems to work really well. Let me encode long-term, short-term types of memory, procedural, declarative, and wire all these together. And now that inductive bias means I don't need to build billions of parameters, and I can emulate a whole variety of tasks all in one architecture. Whereas the connectionist paradigm today doesn't even embrace too much. There is some, and I want to be careful not to say there's nothing. That modularity, those inductive biases, the efficient use of parameters. And I think mortal computation kind of takes it all back and says, what if we were to build the simplest possible circuit to attack a problem, you can get really good performance, even from just one task performance, with more biophysically accurate neurons and spiking neural nets, because my lab works on those and does all kinds of stuff with that. Well, they're not perfect, and there's a lot that you can criticize about them. They are naturally able to encode temporal. Whereas in deep learning architectures with those little neurons that I was explaining, those point-wise neurons, it's very difficult. And that's why transformers exist, because we're just like, we can't do time, so we're going to give it windows of data and chuck it all at once, and that's why they can kind of do temporal-like things. But we're kind of omitting a lot of the biological mechanisms that allow us to efficiently learn from and process in an online way temporal data. And this is just one of many things. And what do I mean by online? It means you and I, when we train, we update every millisecond of our lives, right? It's not, and again, things can change with different timescales. Whereas like deep learning, what you would do, and this was specifically even before transformers, you would take a sequence of data and you would unroll the architecture, copy it over time, and calculate the derivatives to update it. And the joke I have when I teach my students, older deep learning things, is I explain that this would be like you copied your brain several steps in time in a time machine, stitched all your copies together, updated it, and then rolled them back in, and you rinse and repeat every step in time, which is nonsensical and inefficient, and also runs out of memory on computers. Biological entities can operate iteratively online and with very little capacity. So imagine if you could get what you do with transformers with very few neurons, very few subcircuits. Now all that capacity of billions and billions of neurons that we use for transformers could be used for other things. And imagine the complexity of tasks that we could do, not just an array or a suite of tasks, but now we can aggregate subtasks together to do even more complicated tasks. I think if we wanted to get towards even any remote sense of AGI or general intelligence, we sort of need to revisit the fundamental computing units that compose these architectures. And I think biology gives us one very promising place to look to how to build those very powerful and rich computing units, but you could build very complicated architectures. Does that make sense?
I like that focus on complexity and like making these architectures, which, I mean, you could just say, oh, brute force it, make it as big as possible, but it's just like simply, I remember talking with Maxwell Ramstead about how there's only so much like energy in the that we can usefully use in the world, and so many like physical materials to make GPUs and things. And so at a certain point, it's like, if you want to make things as complex and as useful as biological systems, at a certain point you kind of need to go in that direction. Otherwise, like, there's only like a certain amount that you can kind of brute force computation without like, and as well, there's like an incoherence as well. Like, again, you just can't make the same kind of thing if you have like all the neurons. There's a limit to it. Like, we say, oh, it's a neural network, but really like any individual neuron is not really like our neurons. It's a point doing like one kind of function. Whereas like you mentioned spiking neural networks. I don't know too much about them, but yeah, as you say, it's like they can do more such that they're like
temporal data. They're, for example, naturally temporal. They're also very discrete, which is wonderful and then Carl and I have talked about neuromorphic spiking computing as a paradigm for model computation, but that could be its own discussion. But these things are naturally able to process temporal data, whereas you have to do a lot of engineering in deep learning to kind of make it do similar things, and it often does it in an inefficient way. And I think what you were saying about complexity really hits home the point that if we make things bigger and bigger, right, we're using a lot of capacity, but we're learning functions also in a rather inefficient way, because deep learning to get in transformers, we just have the compute to sort of make that disappear. Is they're sample inefficient. You require a ton of data to learn things that and you go back to the beginning of the podcast where you were talking about babies. Babies are beautiful because they tell us really the right paradigm to begin learning. We can learn from one data point, and we can learn general concepts. Now, that doesn't mean they literally use one data point, because statistically that's impossible. Mathematically, you can't learn from just one data point. Babies have this beautiful thing about manipulating and interacting with the world. That data point, that block that it looks at, has all these modalities. It puts it in its mouth, it smells it, it throws it, it touches it, it moves it around. There's a billion data points within that one. And so that baby can build a really complicated generative model of its world with just what you would call one data point. But if I gave that one static image, right, to a transformer or a vision transformer, because transformers are not just language, that thing is not going to learn. And you need to give it millions and millions of examples of images. Why? Because that's how you get the variety that the baby has. But the system itself has no notion of interacting with the world that data point comes from. And that's where it goes back to the whole passive learning thing. So even when you give it more and more neurons and more synapses and more attention layers and all these other mechanisms, they might be important, but at the end of the day, you're wasting this capacity and you're learning these functions that probably could have been learned with an inductive bias that's way more efficient. And then you could use all that capacity, right, to learn more things. And so I think that complexity argument sits at the heart as to the difference between biomimetic intelligence and biological inspired learning, brain inspired computing. There's a lot of words for this. And artificial intelligence, the way that we do it today.
Well, this has been great, and I don't have anything more I want to ask. But is there anything else you want to say, or else where can you point people to find your work?
Oh yeah. Well, first of all, thank you for having me. This was a wonderful discussion, and I hope to chat more. But I would recommend, and you could probably, I don't know if you put links in the captions to your channel, maybe put a link to the Mortal Computation paper that I had you look at, because I think that kind of ties the message up that we've been discussing. And I think that's a good paper for newcomers to look at. I would also recommend anyone watching to look up the Neural Adaptive Computing Laboratory, or NAC lab at Rochester Institute of Technology, if they are interested in all kinds of wonderful work. And they could look at our Google Scholars or our webpage for work on biological credit assignment, spiking neural networks, and predictive coding and active inference. All these other tools that we didn't have time, Jack, to talk about, that I think are important to enabling and building mortal computers. As I see mortal computation as this general theoretical framework, but we need to build it. And my training from long ago is being an engineer. So I like to also answer the question, how do I even begin to build this? So we need more people to work on this. So I encourage the audience to get into mortal computation, because as a new direction that Carl and I have said, changing the field, we need people. We need those that want to go into it, the future generations of researchers. And again, from all domains, the last comment I have on this is that it's interdisciplinary. It's actually transdisciplinary, which is, in my opinion, the strongest version of mixing fields. Economics plays a role in it as well. Physiology, physics, computer science, biology, chemistry, all these things come into play and lead to this intersection of building what is known as mortal computers of all kinds. And even philosophy really has a nice role in this as well. So I think I encourage those to read that paper that hopefully you'll link them to, and to look up the Neural Adaptive Computing Laboratory for perhaps some algorithms that could be used as tools to build computers.
Awesome. Well, thank you.
Yeah,
Awesome.
Thank you, Jack. I appreciate it.